Welcome to Sound 101. First of all, waves travel in a longitudinal way. So it travels this way instead of this way, which is like a transverse wave. The equation for a wave is, whiteboard please, velocity equals frequency times wavelength. Also, sound travels in different speeds. It travels more faster in solids rather than gases. So it goes solids, liquids, then gases. The temperature also determines how fast the sound wave travels. So a higher temperature means that the sound wave will travel faster. But in a lower temperature, like here in Pacifica, the sound wave travels slower. The pitch of a sound is the different tones that the sound makes. So it depends on the frequency. So thank you for tuning in.
So sound intensity is the measurement of how intense a sound is. Okay, so this is the equation for sound intensity. So you can see intensity is equal to the power divided by 4 pi r squared, because this measures like the area where a certain sound is placed. The higher the radius is, the higher the area of the sound, the less intense the sound actually is, because then you're dividing by a bigger number and then the intensity becomes smaller. So intensity is measured in decibels. Humans can only tolerate a certain level of sound intensity. So if you listen to your iPod for too long at a really high volume, that's really bad. But proportion it out correctly. If you listen to it really high for a lower amount of time, then it's a lot better for you. But it's just good to listen to it at low volume constantly, because iPods can reach a dangerously high volume and you will lose your hearing. So what is this machine we have here, Annie?
It's a decibel reader to measure intensity, volume,
We're going to measure the intensity of that 47 hertz wave. So what is it from here?
So it's 80 minus
5.
So it's 75.
Yeah. But if you go closer to it, what happens?
It's going to be 84.
That's really cool. See, so that's just like that equation that shows intensity is dependent on distance. Mm-hmm. So the closer you are, the higher the intensity is.
The Doppler effect. As an object moves, its frequency remains the same. It remains constant. But let's say there's an observer here, observer A, and an observer B. So, as it moves across about 100 miles per hour at very high velocity, observer B hears the moose's meows at a high frequency like meow, meow, meow. But observer A hears the moose's meows at a very low frequency like meow, meow, meow. So, why is this? It's because the moose is moving at such a high velocity that the sound waves are catching up to each other. And so they have a tendency to be closer together. So that makes a higher frequency. That's why it's so high. But as the moose keeps running this way at 100 miles per hour, the waves are farther apart because it's like he's running away from them. So that creates a lower frequency. A better example in life, instead of a moose running at 100 miles per hour, it's very possible though, is a fire truck or a siren or an ambulance when you hear that. So pay attention next time and see if you could hear the different frequencies.
Today we're going to talk about resonance. All objects have a certain frequency at which they resonate. So if you take something like a wine glass and do this, that's the natural frequency of the wine glass. If you were to generate a tone at the natural frequency of this wine glass at a certain intensity, you could actually make the wine glass vibrate or even break. So that's resonance. So instruments actually use resonance to work. So when you strike a certain note or something, the hollow part of the instrument actually has that same frequency. So say when you strike A, like you can actually hear that it's still vibrating inside the instrument. Even if you take like two different instruments, say a guitar and a cello, and you strike this one, this one actually resonates inside the hollow body. It's really cool. So we have some equipment here. We're going to try to make the wine glass resonate by generating a tone that has the same natural frequency as the wine glass.
Mm-hmm.
So this is a program. It's called SMART. It measures the frequency of a sound and the decibel level. So here, all those little blue and green lines are measuring the sound of my talking through this microphone here. Here we're going to try to find the natural frequency of the glass. So, yeah. Okay, try another one. Okay, yeah, I found it. It says it's 1.12 kilohertz. So we have to put that into Audacity and try to make a tone and see if it works.
Frequency.
1120, right? Hello. Okay. So we have that. Do you see any movement?
No.
So our experiment to resonate the wine glass wasn't very effective because our speakers can't put out enough sound pressure to make this actually resonate. But if it were a lot higher, like with a huge sound system or something, it might actually make this vibrate or even break. Yeah.
But we tried.
Yeah. So this is what happens when we did that and put it onto Audacity. You zoom in, you can see the little tiny sine waves that it had created. Then you can actually take the wavelength of them by measuring the length from the top of one wave to another. So now we're going to try to make the tissue vibrate just by generating a really, really low frequency. This is sound at its lowest. Oh. So you can see the tissue vibrating just from sound. This is how high the volume is. It's really high, and yet you can
Getting below the range.
And become like famous scientists,
Yeah.
physicians.
physicists.
Yeah, physicists.